Hello, today we're learning where the electrons are for every element. This determines the line spectra, the reactivity, the size, the magnetism, all sorts of stuff about atoms. So remember we had Bohr models, which are pretty easy to draw, but kind of wrong because atoms aren't two-dimensional, so it's just a nucleus and an energy level. But then with quantum mechanics, the math changed so that atoms are now three-dimensional. And instead of the electron orbiting like a planet around the sun, it's a probability the electrons will be somewhere in that three-dimensional space, 90% probability. So just somewhere in there, I drew a red dot. I started off small, even though it's hard to see because hydrogen is a small atom. And then instead of just calling it energy level 1, this is called energy level 1, and the magnetic quantum number is 0, which means S shape. You don't have to know about quantum numbers. And so S shape you can try to remember as corresponds to a sphere shape. And then if we do helium, it's still going to have the same orbital because the math equations say that each orbital can hold 2 electrons. That helps explain magnetism. And since helium has 2 protons instead of 1 proton, it'll have a bigger attraction to the nucleus. It'll draw the electrons in a little bit, so helium is a little bit smaller, and each orbital can hold 2 electrons, so I've drawn 2 electrons in there. It's still called a 1s orbital because it's first energy level S shape. Then, since only 2 electrons fit in the first energy level, and since only 2 electrons fit in the 1s orbital, we need another orbital. So lithium has the 1s still, and then it has a bigger s orbital, a much bigger s orbital, with 1 electron in it, and that's called the 2s orbital. Beryllium will be the same, except for since it has 1 more proton, the orbitals get pulled in a little bit closer to the nucleus, the electrons get pulled in a little bit closer to the nucleus, and it's supposed to have 4 electrons there. There I fixed my picture so that you can see the electron that was hiding under my line, and so the 4th electron will be somewhere in that 2s orbital. So that's 4 electrons. Now we might have learned before that the second energy level can hold 8 electrons, so we can't just add a second energy level. We just can't add a 3s orbital, because that would be in the third energy level, so we have to have more orbitals that are in the second energy level. So the math equations say that these aren't shaped like spheres. They're shaped like this, so a propeller shape. So this one has 1 electron in it. Each orbital can hold 2 electrons. It could be anywhere there in that whole orbital. This is 1 orbital. Kind of looks like 2, but it's just 1 propeller shape. And that is called a 2p orbital. 2 because it's second energy level still. P corresponds to the shape. You can remember that it corresponds to a propeller shape. Okay, next, I think this is as far as we got last class, is that we have 6 electrons we have to put somewhere. And so far I have 5, so you might expect the 6th electron to go somewhere in this 2p orbital, so it has 2 because it can hold 2, but see how much skinnier a p orbital is than an s orbital? When it has 2 electrons in the same orbital, they repel each other, and that's not as stable as if they're farther away from each other. So it turns out there's 3 possible orientations of 2p orbitals, and they all have the same energy. So each 2p orbital gets 1 electron before any gets 2. That's called Hund's rule. So we're going to put the next electron in a different p orbital. So if the first one points up and down, this one points left and right, or front and back is the ways it can go. So I'll put another electron somewhere in there. That's also called a 2p orbital. And then for nitrogen, we have the same drawing so far, but then the last electron goes in a third kind of 2p orbital. There has to be 3 kinds of 2p orbitals to hold 6 electrons total, so that the 6 plus the 2 that are in the 2s add up to 8 to fill up that energy level. So then now I have 3 2p orbitals, all just with a single electron in it. That's kind of interesting for magnetism because this predicts the magnetism of these atoms to be paramagnetic, which is attracted to a magnetic field, where if all the electrons were paired up, it'd be diamagnetic and repelled by a magnetic field. We'll talk about that a different day. So then, once each p orbital has one electron in it, then you start doubling it up before you go to the third energy level, because the third energy level is a lot farther from the nucleus, so it wouldn't be as stable that way. So oxygen would have 2 electrons in one of the 2p orbitals. So there it is. I've drawn 2 in this one that goes up and down the z orbital along the z-axis. Fluorine would have 2 electrons paired up in 2 of the orbitals. And then finally neon would have all electrons paired up in all the 2p orbitals. If we were going to go to sodium, then we would have to add a 3s orbital, which is way farther from the nucleus, and then the atom would get a lot bigger. Check out the sizes of these atoms. I've tried to draw them more or less to scale. So you can see in the first energy level, you start bigger and then get smaller because you add protons that draw electrons in. Same thing with the second energy level. Start bigger. As you add protons, atoms get smaller because they draw the electrons in. But neon is still bigger than hydrogen. I've drawn mine a little bit bigger in real life. It's about 3 times the size. So hopefully that helped you understand what we're doing and saying which orbitals are all the electrons in and what the orbitals mean and how they look in an atom. You never have to draw these, so it's good for understanding. But when you draw, we're actually going to do a shorthand notation that means these things. Before we do that, to help you with the patterns we'll start looking at tomorrow, check out how these sizes basically would affect the reactivity since we have these atoms in front of us. So fluorine, you might have remember, likes to gain an electron and form a -1 charge. That's because for its size, which is pretty small, it has really a lot of protons. It has 9 protons. So these electrons that are right here have a super high attraction to the nucleus because for its size, again, it has a big positive charge in the nucleus. So that means that fluorine has a really big attraction to an additional electron, so that makes it really reactive. Along the same lines, neon is stable because it has all these orbitals filled up here, and if it were to gain another electron, the electron wouldn't be here and be really attracted. The electron would have to go way out here in a third energy level, and then it wouldn't be very attracted, so that's not going to happen. Lithium here, because it has a big size for how many protons it has, because we just added a second energy level, this electron out here in the second energy level is not very attracted to the nucleus. So it's easy for lithium to lose that electron, so that's what it does when it reacts. Okay, so nothing so far that you really have to know. We'll learn more about the reactivity and size patterns later. So we just learned a pattern so far, really is all there is to this. So let's do the pattern again. The pattern goes, you fill up the 1s orbital with 2 electrons, then you fill up the 2s orbital with 2 electrons, then you fill up the 2p orbitals with 1 electron each, and then with 2 electrons each. After that, it goes 3s, and then the 3p. The pattern keeps going like that. Okay, so let us do some orbital diagrams. Orbital diagrams, also called orbital notation, is where you draw a line to represent an orbital and you draw an arrow to represent an electron. So, hydrogen, you would draw a line to represent an orbital. You would draw 1 arrow to represent hydrogen's 1 electron. The 1 refers to the energy level, the S refers to the shape. Next, we'll do helium. So it would have a second electron in the 1s orbital. When you have 2 electrons in the same orbital, you draw the second one with the opposite direction of arrow to show that the electrons have opposite spins, which is important for magnetism. That's called the Pauli exclusion principle. The electrons in the same orbital have opposite spins. And so then lithium, we need a new orbital because each orbital only holds 2 electrons. So that'll be the 2s with 1 electron. Beryllium, all the electrons will be paired up, so that'll be diamagnetic. Boron, we need another orbital, so that'll be one of the 2p orbitals with 1 electron in it. Carbon, we'll have some of the other 2p orbitals with one electron in it, whereas boron have these other 2p orbitals empty. You can just draw one of them, or you can draw all three and show the other ones are empty if you want. So those are all called 2p. So carbon will have then the second electron not in the same orbital, because that would repel too much and not be as stable for all these having the same energy and being the same distance from the nucleus, as having a last electron be in a different orbital. So that makes carbon paramagnetic instead of diamagnetic, because electrons are unpaired. So you can see that elements in a group like hydrogen and lithium have the same number of valence electrons, one valence electron in the first energy level, one valence electron in the second energy level. So again, that makes elements in a group have similar properties, for example, hydrogen and lithium, because for their relatively big size, they have a low number of protons. Or if you go on the opposite side of the periodic table, for their relatively small size, they have a large number of protons. So then you see that there's a pattern. It goes 1s, and then 2s fills up, and then the 2p's fill up with 1 each, and the pattern keeps going within 3s and 3p. You can, so this is all there is to electron configurations is memorizing, but that's kind of a pain. So it's easier to look at the periodic table and memorize a couple of things instead of memorizing the whole pattern. So on your periodic table, please draw in these labels. So first move helium over here, because it's in the s orbital. Label these first two columns, first two groups, the s block. Label these 6 groups on the right, the p block, because there's 3 p orbitals. They can hold 6 electrons total. Label these ones in the middle, the d block. That's the next kind of shape for orbitals. Label the ones at the bottom, the rare earth elements, the f block. So that's one of the 2 things to memorize to figure out the pattern that orbitals fill in. The other thing is just the numbers. So the periods on the periodic table correspond to the energy levels. So 1 for hydrogen, helium, 2 for lithium, beryllium, and all the way across. And 3 going down, except for when you get to the D block and the F block, the numbers don't match like that. Because in an energy level, each type of orbital has a little bit higher energy. So like 3s is lowest energy in the third energy level, and then 3p is a little bit higher than that, and then 3d is a little bit higher than that, so they each get higher like that. 3d actually winds up being a little bit higher in energy than 4s. It's kind of weird, but it's just math equations. So the period number corresponds to energy level, except for when you get to the d's, they drop down 1 less than you expect. So this is 4s here, but then 3d. And then the F's drop down 2 energy levels. So this is 6s here, but when we get over to the F's that fit in right here, they're 4f. So the F's fit in right after the first 5d, and right after this first 6d, and then when we get back to the P's, it goes back to normal. So this is called the off-bell principle, that the electrons fill the lowest energy orbitals first, the off-bell principle, and the pattern goes 1s fills up first, and then 2s, and then the 2p's, there's 3 of them, and then 3s, and then 3p, and then 4s, and next comes 3d, and then 4p, 5s, 4d, 5p, 6s, 5d1, just the first electron in the 5ds, and then the next element goes in the f's because it's the next number is down here. So then 4f, and then the other 9 5ds. There's 5 kinds of d orbitals, 5 orientations, 5 directions, and then 6p, 7s, first 6d electron, and then 5f, then the other 6d electrons, the other 9, and then the 7p's. And that's all the elements on the periodic table. So it's kind of weird pattern. There's not really anything to understand. Remember, it just comes from math equations. There's a figure in your book that shows how the orbitals kind of overlap to give the energy orbital. And I'll show you a different way to memorize the pattern tomorrow if you don't like this way. And now let's practice. So that's really all there is to this, is the pattern. So what would the orbital rotation for zinc be? I'm just taking time to draw this again. You can just look at your periodic table, it's better. So zinc, you can just find it on the periodic table, ends in 3d10. So we're going to just go in that order. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and stop, because that's zinc. You can also know to stop because you'll have filled in the number of electrons that it has. You'll have that many arrows. So I'll go ahead and do all the order that I just said. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. We don't have to do because it's zinc, so we're starting on 3d. Notice I'm filling up the p's. Each orbital gets 1 electron before any gets 2. I'll show you again. Being lazy and not drawing all my arrows, but if we're here with each of the 2 p's having 1, then you go back and double them up. 3 p's, each one gets 1, then you go back and double up. 3 d's, each one gets 1, then you go back and double them up. And that is called orbital notation with the arrows. I was lazy and kind of didn't draw both sides of my arrows, but they're supposed to be arrows. So, in your book, the first problem, when it says, I think, orbital diagram, this is what they mean, draw arrows for orbital notation. Okay, a faster way to do this, but it doesn't show whether electrons are paired or unpaired, so it doesn't show magnetism very well. It's just called normal electron configuration. That's with superscripts. So electron configuration, you would use superscripts instead of arrows. You say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And finally, the fastest way to do these is called noble gas notation. Noble gas notation is where you put in brackets the symbol for the previous noble gas. So even if you're doing a noble gas, you have to go back to the previous noble gas, and that represents the electron configuration of that noble gas. So for zinc, you go to the previous noble gas, previous an atomic number, and that is argon. So in brackets you put argon. That means 1s2, 2s2, 2p6, 3s2, 3p6. That's argon with 2, 4, 10, 12, 18 electrons. And then you continue on from there. So we do 4s2, 3d10. You can also do noble gas notation with showing the arrows. Okay, let's do one more example that's reverse. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Which element would that be? So 2 ways to do it. You can look on your periodic table and know that the 3Ds are this first row. So you go and you find it right there. Or you can count, let me go back a little bit, or you can count the number of electrons. So you can just say 2, 4, 10, 12, 18, 20, 28. You just find number 28 on the periodic table. It's nickel. Next question, how many valence electrons does it have? So you need to count all the electrons in the highest energy level with electrons in it, because that's the definition of valence electron. So it's not these. In fact, sometimes these are written over here instead of in the order they fill in, so you'll see it both ways. But it's the ones that have are in an orbital starting with 4, because that's the highest energy level. So it's just these 2. 2 valence electrons, all the ones with the highest number. And what would the magnetism be? So paramagnetic means it has unpaired electrons. Diamagnetic means all electrons are paired up. So it's kind of hard to see with this notation. It would be easier to see with the orbital notation to see that the electrons are all not all paired up. So it would be like this one, except for these last two here would not have doubles in them, just single electrons. Okay, finally excited our ground state. So if it's called ground state, if all electrons are exactly where they should be, according to the Aufbau principle, in the lowest energy orbitals possible, if you see something weird, like it said like 4s1 and then it had a p over here or something like that, so some of the electrons had jumped up to higher orbital or higher sublevel or higher energy level, that would be excited state. So this one is just how you would expect, so it's ground state. So I know that was a long video. I know this seems tricky. Remember, it's just really an order. So order goes 1s, 2s, 2p, 3s, 3p. That's easy, right? And then 4s. And then after the 4s, start coming the d's and they drop down one energy level. And that pattern repeats. And then after 6s and 5d, then you start adding the f's. So that's why looking at periodic table, I'm just memorizing where the S, P, D, and F blocks are, and that D's drop down 2 energy levels, and the D's only drop down 1 energy level, and F's drop down 2, makes this easy because that'll give you the whole pattern.